Hey guys, Mr. Palmer back with part 3. In this one, I'm just going to do a quick problem and look at what happens when we are approaching the equilibrium point but not quite there. And the last video, you go back and look at that one if you haven't seen that one. We looked at how we do it at the half equivalence point, and we compared a strong acid to a weak acid in the titration. On this chance, if we read this sample, I've used a lot of the same information, except you'll see that I have changed this one now, right? It's different from the last one. We're mixing 50 milliliters of 0.1 molar acetic acid. The acid's the same, but now I've added 40 milliliters of 0.1 sodium hydroxide. In the last one, it was 25. So we were at the half equivalence point. Now we're at a point that's past the half equivalence point. So if I was looking on my graph, there would be my half equivalence point. Now we're something close to, but not quite at the half, or not quite at the equivalence point. We're somewhere in this region. So we're going to be using the Henderson-Hasselbalch at that point. There's some amount of acid, and there's some amount of our conjugate base. We're going to find those moles, find their concentration, and determine the pH at that point. Okay, so let's go back into it. Like we did before, we're going to do molarity times volume, and that's going to give us the moles of our acid and base. So for my acid, it's the same as it was before. That's 0.005 moles, ICF. Okay. The base now, I've got 40 milliliters. So 40 milliliters times 0.1 molar sodium hydroxide is going to give me 0.004 moles. Again, we're not looking at the water. The conjugate base starts at 0. Limiting reagent is still going to be the base. We're not at the equilibrium point yet. So we still have leftover or excess acid in the solution. So when we do this, we're going to say, all right, limiting reagent, we use up all of it. It's a 1-to-1 ratio, so we're going to have the same amount of acid be eaten up, right, be used up. The conjugate base, again, 1-to-1 mole ratio, so this is going to go up by that same value, 0.004 moles. So that's going to leave us with 0.001 moles of acid, no hydroxide, because that was our base, the limiting reagent, and that's going to give us 0.004 moles of our conjugate base. Now, to do this equation, we've got to turn these into concentration. We can't use the Henderson-Hasselbalch with moles. We need a molarity. So we got to divide these by the total volume. Let's go back up into the problem. We had 50 milliliters. We added 40 milliliters. That's 90. So if I divide this moles over the volume, which would be 0.09, this one's going to be 0.09. That's going to give us a molarity of our acid of, what's that going to be? 0.0111. And our conjugate base would be 0.0444. We're going to put those numbers up into our Henderson-Hasselbalch equation. Now, in the last problem, you saw that we already found the pKa by taking the negative log of the Ka value. So negative log of 1.75 times 10 to the negative fifth was 4.757. All right, you can just do that if you haven't already. And we're going to do the log of, well, what's the log? It's the log of 0.0444 over 0.0111. That's just going to come out to be 4, right? That's what we're going to get there, which is 0.602. So that's going to give us a pH for this solution of 5.359. Where is it? Well, look, it's a little higher than our pKa. On our titration curve, if we go back, where are we during this region? A minus is greater than the conjugate. This region down here, the HA is greater than the A minus. At that point right there, we did the half equivalence point. They're going to be equal to one another. Okay? So we were here in this region. I'm going to pause that there, and I'm going to come back and do this last one. The last one we're going to look at is what happens when we are at the equivalence point. How are we going to calculate that pH?